Our next speaker is Miruna Oprescu from Cornell University. She's a computer scientist working with Nathan Callis. She did her practicum at Brookhaven National Laboratory, and today she's going to tell us about beyond prediction, when machine learning meets causality.
Thank you. Hello? It's working? It's working. Hi, everyone. If you don't already know me, I'm Miruna, and today I'll be talking about machine learning and causality. So before I get started with some of the work I've done during my thesis, I'll first use the first 5 minutes to talk about causality and why it's important. So most of the modeling that you probably do in your day-to-day work is this kind of predicted modeling, when you're trying to predict the outcomes in some data set to the best of your ability, right? So you should be pretty familiar with this. Causality, though, is a very different problem with a very different set of questions. And in causality, we usually ask, what if we act, instead of what will simply happen next. So this includes questions like, what would change if we acted, which variable changes the outcome, and if some policy would work somewhere else, and et cetera. So these are the kind of difference between prediction and causality. And the funny thing is that you can use the same data set and get opposite conclusions, depending on how you look at it. So let's think about this example for a second. And let's say we have some hospital records. And what we see in our hospital records is that people who receive more intensive treatment, they have worse outcomes. OK, so from a predictive standpoint, this is actually correct. And it is useful. So we can flag patients who are at higher risk and then monitor them for longer. But if we use this observation to then enact a policy change, let's say, the outcome here would be that the policy is to withhold treatment to improve outcomes, right? Because worse, more intensive treatment means worse outcomes, then less treatment should mean better outcomes, right? So if we naively go and use this predictive model to then make a policy about who you should treat more intensely, you will reach a catastrophic conclusion that we don't want, right? And this is probably obvious to anyone in this room, that you would see this data and you would not make this conclusion. You would not go to a hospital and say, we should treat sick patients less. But there are a lot of examples out there, like healthcare, climate and environment, grid and energy systems, scientific discovery, AI systems, where we don't have this intuition, right? We build a machine learning model, and we cannot look through it and understand whether what it's finding, it's useful for also implementing these changes, policies, interventions, et cetera. OK, so where do I come in here? So my work is about bridging machine learning and causality. So again, machine learning is extremely useful. It can generalize to really large data sets. It can take in all sorts of data. And we love that it's flexible and scalable, and it does really well on a lot of different applications. However, when in the last decade or so, we moved from structural modeling, from equations and physics and constraints, to machine learning, we left something behind. And that's this causal structure of the world, these mechanisms, understanding of the mechanisms in your data that lead to your data generating process. And this is, I put it all under causality, but it leads to a lot of fragility. Like, these models are not particularly robust under shifts and interventions and things like that, OK? So my goal here is, though, not to reinvent machine learning. It doesn't work that way. I really don't have that much time, right? So my work is somehow connected to. So in my work, I use causal structure to define the right question that we want to answer, and then, to the best of my ability, reduce it to bits and pieces of machine learning that then I can use off-the-shelf modern machine learning to solve. OK? So that's what I'll be talking about for the rest of this talk. And if you do causality right, so Brian earlier was talking about the fact that we know what happens in good regimes, but we don't really know what happens when we have disruptive events. If you do causality right, you should be able to tell what happens under disruptive events that have never happened before. Okay, so that's kind of the point. Okay, and also thanks to Brian that he already brought up forest fires, because our running example here will be wildfire smoke and respiratory health in California. Okay. So just to have an example as we go through some of the techniques that I'm working on, We'll talk about this example of wildfire smoke and in California. So in California in 2018, there was a wildfire season with 2 really big fires, forest fires, right? We see that as the smoke goes up, quantified by PM 2.5, which is this particulate matter that's greater than 2.5 microns, the number of respiratory illness cases has also gone up, right? You can see it on the, let me see, I'm going to test this. Okay, cool, it works. So you can see here that during the fires, the respiratory illnesses are going up, right? So we see this, but it's really hard to say that the cause of this is the wildfire. So the reason for this is that, yes, there could be causation that wildfire smoke causes respiratory illness, but it could also arise purely due to correlational relationships. So for example, maybe the fire happened in more vulnerable places, or maybe there was already a pretty bad flu season, for example, in November, and cases were on the rise regardless of the wildfires. So the question here is like, how much of this increase in the respiratory illnesses is actually attributable to the fire, and how much because of other stuff that was happening in California at the same time, right? So I want you to think about this as we get more and more technical over the next 10 minutes or so. Okay, so this example is one of, it's very difficult. It's one of these complex systems that I talked about at the very beginning of the talk. And the reason for this is that you have all of these different things happening. Like we have space and time, and they are intertwined. We have dynamic feedback, so the actual presence of the fire changes atmospheric conditions like humidity and nearby temperature and things like that. So if you were to train a predictive model and you're saying, oh, and now I'm going to look at California, but turn down the fire in my data set and predict on that new data, that's not quite right because a lot of things change because of the fire in California in those times. And the last thing is unobserved factors. There's a lot of things that could make correlations look like causation that we might not be observing because we don't collect all of the data about what happened in California in 2018. So we're going to figure out how to solve all of this, basically, step by step. So we're going to first talk about space-time and this dynamic feedback, and then I'll talk about the second piece of work about the unobserved factors. So for the first part, and these are some equations here. There's no way around it, truly. But first, we're going to talk about this causal recipe for dynamic systems. So dynamic feedback is this issue where past conditions affect future conditions and exposure, like, for example, smoke exposure. And then they in turn affect future conditions. So you can see that weather can affect how the smoke disperses, but the smoke dispersion affects like weather conditions next, right? Like it affects humidity in the atmosphere. And that's problematic because like, okay, humidity also affects pollen dispersion and people might get more asthma attacks. So we don't really know if was it the wildfire that caused people to go to the hospital or the asthma attacks, right? And the idea here is that in classical causal inference, without any machine learning, people have figured this out through this procedure called an iterative G computation. And it's a pain to explain, but I'm going to do my best in like a minute to tell you all about this. So as you can see here on the bottom, this is just one time series, not all of California, right? So like you see everything until the fire, and then you're asking what would have happened under no fire, and then there's all of these potential trajectories, right? Because we don't know how weather would have evolved. Things are kind of unpredictable, so these are all possible things that would have happened. And to find the answer to this dynamic feedback, what we have to do is this nested integral over all of these time steps where the fire happened, using this like conditional probability distributions that are very high dimensional, right? So that's the solution, and that's not something I figured out. But it's a very, very difficult thing to estimate because it has these probability distributions that are very high dimensional. So our insight here was that this actually instead can be written as a set of nested expectation, nested conditional expectations, which are much easier to estimate because I don't have to learn a whole conditional distribution. All I have to learn is the mean. That's the conditional expectation, right? And most importantly, expectations is something that we can turn into a predictive model. Machine learning, if you use root mean squared error, for example, like mean squared error as your metric of choice, its optimum is a conditional expectation, right? So now we can throw machine learning at the problem when we can write it this way. And the way we end up doing this, and I won't go into a lot of detail here, but basically now we can take this causal recipe or this causal insight and turn it into a deep model. And basically, we noticed that all of these iterated expectations are basically tasks that are related, and they depend on each other. So you have to solve the first task in order to be able to do the second task, and so on and so forth. Luckily for us, machine learning folks have already solved the problem of multitask learning with dependent task. So we can just borrow from that literature and build our causally adjusted or causally meaningful model. So by starting from this predictive spatiotemporal model and adding these tasks that represent those iterative expectations in order to make it causal. And the solution here, we call our model GSUNet because it's G computation, spatiotemporal, UNet, whatever. We were not very creative here. But basically, we see that as we increase the dynamic feedback strength, a lot of these models, competitive, our baselines, incur a little bit of, oops, I'm covering this. Okay. A lot of bias, whereas our model basically stays kind of static over time. So. Okay, thank you. So you can see that, and this is all the RMSE is with respect to the ground truth causal effect. So we can see that we can get a bias, a small error in our causal effect, whereas this model is just accumulated as this dynamic feedback strength increases over time. Okay, and then the second problem that we talked about is these hidden factors, right? So we cannot observe everything that happened in California. So what if one of the things we observed, like the state of the population health already, or the flu season, or whatever, that we don't have data on, actually affected both, the wildfires, it affected the health outcomes, and it could lead to kind of spurious correlations in our data, right? So how do we get around that? And this is kind of an interesting tidbit. So in classical approaches in causal inference, you can try to reconstruct hidden factors by looking at multiple interventions. So let me give you an example that you might be more familiar with. If I look at your movie streaming history or your music listening history, right? Maybe I don't know what genres you're listening to, but I can look at a few songs and kind of infer what kind of music you like, right? So I'm able to reconstruct this unobserved factor, which is the genre you like, just by looking at the kind of things you do. It's the same thing in causality. Like if you have multiple things that happen at the same time, they could give you some signal about these unobserved factors if we believe they affect all of these interventions or exposures that are happening. In the climate environmental data that I'm using, you have a fire, but it's very unlikely that you'll also have a tornado, economic collapse, and a lot of other these things that we can maybe use to build these unobserved factors. So instead, we're going to leverage something called interference, which is the fact that if you are at one location, you're affected also by you're affected by what happens around you in the locations nearby. So smoke levels at nearby locations would affect you at this location, and due to transportability or the fact that you seek medical care in another county and things like that. So interference gives you this for free in spatial settings. And you can see here on the right-hand side, humidity, which you can treat as one of these hidden factors, although usually we measure humidity, and PM 2.5 exposure, and they're very correlated. So you should be able to reconstruct one from the other. Okay, and then we did this. We call our method the spatial deconfounder. Again, I really need to find better names for our methods, but we know that machine learning has a lot of methodology to reconstruct these latent confounders, latent spatial confounders. So we use a conditional variational autoencoder. I'm not going to go into the detail of what that is, but basically that plus a prior can reconstruct this kind of hidden field using this multiple intervention approach to this problem. And indeed, it does much better than a lot of the other spatial methods that we compare with, and we can reconstruct these vectors. You can see, latent space is pretty high dimensional. This is just the first principal component, but you can see they're very correlated. So. And I'm running out of time, so if this seems like I'm kind of running a marathon, it's because I am. But I want to show you what actually ended up happening in the wildfire smoke example using the two methods I just talked about, and then I'll just conclude then. So this is the fire. We didn't have a lot of features, so it's, again, very important to reconstruct these unobserved factors if we can. And then because there were 2 fires, we could use one for training and one for kind of prediction. So that's, I guess, good and bad at the same time. There were 2 fires in 2018. So our methods estimate that during this 10 days of the campfire, so that's the second fire, the smoke contributes to an excess of 4,600-ish, so 460 per day, respiratory hospitalization in the affected counties. So that's compared to like what would have happened without the fire, right? And to compare this, the predictive baselines grossly overestimate this, because again, the cases were on the rise and things are happening and things like that. And then some other methods, they use more like economic models, but they don't have a lot of granularity of what happens over time, estimated a number way closer to ours. So we have some idea that we're in the more correct ballpark than the naive predictive baseline. But again, there's no ground truth with a lot of these causal questions. Okay, so it is time for me to conclude. I will leave you with a few takeaways that I'm not going to have time to talk about, but I'm hoping that this talk, this 15-minute, very brief overview of my work, convinced you that causality is important, that causality for these complex systems is particularly tricky, and we need to think about it right. HPC is what made this possible and allowed me to like exist in this niche that's very unexplored. And huge thanks to the fellowship. This is all work with the folks at Brookhaven Laboratory, and I use Perlmutter a lot, so I decided to put it there because I live there basically. I live on Perlmutter these days. That's it. Thank you very much. Thanks for listening.